Hello everyone, my name is Carlos. I will be presenting today on the multi-model resilient observer under false data injection attacks. The authors are Benga, Moses Anubi, Charalambos Konstantinou, me, and Satish Vedula. Existing resilient observers rely on the physics side of the model, but cleverly crafted false data injection attacks can bypass that physics-based detector. Now, integrating cyber and physical models for resilient estimators can be a challenging problem. As we can see in the figure to the right, the power system has a corresponding communication network, which routes the system measurements to the control center. It is at this point that the network can be maliciously attacked, corrupting the estimations used for the control of the system, potentially destabilizing it. In the bottom figure, we can see that there are multiple approaches to resilient observers. For example, the ones based on Kalman filter, L1 minimization, or machine learning. Our focus is on concurrent models, which can improve the state-of-the-art resilient estimators because they leverage both a data-driven model for the cyber side and a physics-based model for the physical side. The data-driven model gives a prior distribution on the system measurements as a function of the measured auxiliary variables. This motivates the use of concurrent models because it provides extra layer of security by one, requiring the attacker to know the auxiliary model and its parameters, and as well as limiting the magnitude of possible state corruption. As we can see, the traditional error correction problem can be casted as a compressive sensing problem as seen on the top right. The non-convexity of the L0 minimization makes it difficult to solve for in polynomial time. As a result, an L1 minimization approach is normally used, as long as the restricted isometric property holds. RIP requires that every set of columns with cardinality less than S behave like an orthonormal system, which means that the matrix is guaranteed to only change the length of any vector x very little, as long as the vector x is at least S sparse. From here, we can then formulate a globally convex approximation of the moving horizon compressive sensing problem with the RIP condition, the linear time invariant system model, and the auxiliary data-driven model. The equations to the right show the quadratically constrained basis pursuit problem, where y of t is the vector of historic system measurements after being attacked, u of t minus 1 is the vector of previous control inputs, x is the decision variable to be estimated, which must follow the LTI system model, zk is the auxiliary variable at time k, ht contains the linear relationship between the history of inputs ut minus 1 and its corresponding system measurements before attacks. Phi t contains the relationship between the decision variable x and the corresponding system measurements before attacks as well. The objective is to minimize the error between the attacked measurement vector yt and what should be the true system measurement given by ht ut minus 1 and phi t x. What's left from here is the sparse attack vector e, which we will cover later. It is subject to a quadratic constraint. This ensures that x will have a high likelihood according to the auxiliary model prior. The likelihood is controlled by the quantile function of the chi-squared distribution and the parameter tau. Some of you may be wondering what an auxiliary model is at this point. In the context of power systems, one can think of market variables such as locational marginal price, marginal cost losses, and marginal cost congestion. Now it's how they're correlated to the active and reactive power what makes them an auxiliary variable. The optimization problem presented in the previous slide is used for our numerical studies presented further. It's able to return the estimates of the state vector. And the most recent states are estimated using a physics-based model and forward propagation of the states. An equivalent optimization problem can be seen here. If a receding horizon T is large enough and the AC pair is observable, then there exists a matrix Ft such that Ft times phi t is equal to 0. Here, we minimize the L1 norm of E, subject to the recently stated constraint and the data-driven quadratic constraint. Note that the following formulation is used for in the proof in the main theorem, which is stated next. Given a dataset D containing the historical auxiliary variable Z and the corresponding sensor measurements Y, and suppose that the sensor measurements Y satisfy the data-driven GPR prior given, and that there exists a constant tau between 0 and 1, such that the probability of yk star given the auxiliary variable and the data set is greater than tau. Now, letting E hat be the solution of the previous optimization problem, and if the restricted isometric constant from the previously mentioned matrix Ft is less than 1 over square root of 2, then for any feasible sparse vector E, the true norm of the estimated sparse vector minus the true sparse vector is upper bounded, thus ensuring that we get the best estimate of E. Note, exact recovery is guaranteed if the restricted isometric constant is less than 1 over square root of 2. A rough sketch of the proof is as follows. The probability of yk star given the auxiliary variable zk and the data set D is greater than or equal to tau. This implies a quadratic inequality, which is a function of the composite measurement yt corrupted by the sparse attack vector et, as seen on the top right. This was alluded to previously as well. From here, the true measurement vectors y star t is a function of phi t, which is equal to 0 when multiplied to ft. Then, using theorem 1 from the paper, we know that E hat satisfies the following inequality. With both the stated and the quadratic inequalities, we can arrive at the stated conditions for the main theorem. For the numerical simulation, the IEEE 14-bus system with 5 generators is used as seen in the top figure. The linearized generator swing equations and power flow equations are given in the middle equations. They are linearized based on the following assumptions. Voltage is tightly controlled at their nominal values. Angular differences between each bus is small. Conductance is negligible, therefore system is lossless. Here, in the middle matrix, we can see that LGG, LLG, LGL, and LLL come from the admittance weighted Laplacian matrix. M, the diagonal matrix of inertial constants for each generator. DG is the diagonal matrix of dampening coefficients. The state variables consist of the generator rotor angles delta, generator frequencies omega, the bus voltage angles theta. The control inputs are the generator, the mechanical input PG with an inner PI frequency regulation, and the bus active power demand PD. It's important to note that the model can be reduced to a system of two states as seen in the bottom equations here. Due to the algebraic equation of the bus voltages, reduced system state variables are the generator rotor angles delta and the generator frequencies omegas, where P node is a function of the system incidence and susceptance matrices. The measurement channels consist of the generator frequencies used in the PI feedback loop and the net power injected at each bus expressed as Pnet. Before moving to the auxiliary model, we briefly discuss the Gaussian process regression. It is a non-parametric Bayesian approach to regression. In GPR, we assume a priori function of mean and covariance. We then calculate the posteriori using the training data. Here, the auxiliary model uses the data collected from the New York ISO to build the GPR, which maps the market variables to the load data. For the scenario here, the covariance matrix obtained from the trained data is used to locate the mean within 3 standard deviations from the true value. As for the threat model, a max of 30% of the measurement can be attacked by false data injection. In the bottom right figure, we can see that the bad data detection residual is well below the 5% threshold used in the simulation. This implies that the attacks have gone undetected. The multi-model resilient observer is compared against the Leuenberger observer and an unconstrained L1-based observer. As mentioned previously, the simulation scenario was set up such that each observer was subject to attacks on 30% of the available measurements. The attacks are triggered after 200 samples into the simulation, as can be seen here. The leftmost plot shows the states without the false data injection attacks. And as in the Leuenberger observer, we can see that it is unable to reconstruct the actual states under a false data injection attack. Using these state estimations would be extremely undesirable. The unconstrained L1-based observer can reconstruct most of the signals. Now, if used in a cascaded controller, it could potentially lead to instabilities. Here, the estimated generator rotor angle delta is used for comparison. The multi-model observer outperforms both previous observers, as we can clearly see. It accurately reconstructs the state estimations due to the information provided by the auxiliary model, providing a much better estimation than the unconstrained L1 observer. To quantify the efficiency of the observer, a performance analysis consisting of the root mean squared error and the maximum absolute error is performed. As we can see in the table to the right, the RMS metrics quantifies the errors between the estimated and the actual values. And the maximum absolute metric captures the worst case performance of each of the observers compared. In both cases, the multi-model observer does, if not equal to, better than the other observers. In conclusion, a novel data-driven constrained L1 minimization-based observer is developed. Here we can see in the figure to the left our current implementation. For future works, the multi-model observer can be used as a filter, which feeds the estimations to a cascaded controller, as seen in the figure to the far right. A more sophisticated constraint can be implemented instead of the quadratic one used in our work, and the effects of false data injections under system uncertainties is also yet to be studied. Thank you everyone for participating in this presentation. I hope you have found it both enjoyable and informative. For more information, please contact Moses at anubi@caps.fsu.edu. Thank you very much everyone, and stay safe.